Hi, welcome to the Tau Performance System module in our ALCF Computational Performance Workshop. The Tau Performance System is a parallel performance framework and toolkit, and it includes support for instrumentation, which is adding hooks to your program, measurement for generating profiles and traces, as well as analysis tools such as ParaProf and Perf Explorer. It supports a variety of languages like Fortran, C, C++, Python, and it can use a variety of different runtimes like MPI, OpenMP, and it supports pthread, OpenMP, and even GPU execution models. So you're wondering, what can Tau show you? It can show you how much time is being spent in each application routine, and at outer loops, within loops, it can show you at the statement level, and it can even show you the time spent in OpenMP loops. It can show you hardware performance counter data. It can show you memory usage of your code, how much energy is used, I/O, even the contribution of each phase, and how the application scales. So the first part of Tau involves instrumentation, which is adding hooks to the code to perform those measurements. Now, Tau can add hooks to your application by parsing the source code using a preprocessor, using a toolkit called the Program Database Toolkit, or PDT, where we can parse the source code written in C, C++, Fortran, and recompile that code using Tau shell scripts like taucc.sh or tauf90.sh. And we can add hooks to a copy of the code. We can use a selective instrumentation or a filter file to reduce the overall runtime overhead and narrow the instrumentation focus. So you can say, I want to instrument only these functions and not these other functions, or add instrumentation at the level of loops to these functions. We can also use the compiler to insert the hooks directly in the object code using the same kind of compiler scripts with a separate option of opt-comp-inst to use compiler-based instrumentation. But there is a third option which requires runtime preloading of Tau's dynamic shared object, or DSO. And here we can just launch an application which is a dynamic executable with the Tau exec tool. To use this, you just need to link your program with the -dynamic flag on Theta. Cray systems typically require this so that they create the dynamic executable. On Linux x86-64, it's the default. But you can essentially take an uninstrumented binary and launch it with Tau exec to generate the performance data. What can you generate with Tau? You can generate profiles as well as traces. Now, while profiles show you how much time was being spent in your application at the level of each routine, profiling represents the summary statistics. It shows you the total time spent in a loop or a function like MPI barrier. Tracing, on the other hand, can show you when the events take place on each thread of execution. So you can see along a timeline display what each process or rank in your MPI application was doing. So while profiling shows you the total summary of the time spent in each routine, tracing highlights the temporal variation or shows you when the events take place along a timeline. And with profiling, you can generate both inclusive and exclusive values. So if you consider a function, say foo, which calls an instrumented function, say bar, and it takes, say, 100 seconds in foo and 20 seconds in bar, then the green part here in this figure shows you the total execution time in foo, which is 100 seconds, and the orange part represents the time spent exclusively in the function, which is 80 seconds. So to collect this data, you can either insert probes directly in your code where you have a start and a stop call, and it gives you fine-grained control and precise measurements by inserting calls into your code. Or you can use indirect sampling-based methods where you don't need to modify the code. It requires minimal effort, but it relies on some debug symbol information. This is typically inserted by the -G flag in the compiler. So with sampling, we run the program and it is interrupted periodically by some timer interrupt generated by the operating system, or it could be through the overflow of some hardware performance counter data. And then based on this collected samples, you can then attribute the time. In instrumentation, on the other hand, we insert the hooks by the start and stop calls, and you can see exactly when a particular function begins and ends. And it gives you much more detailed information, but the disadvantage is that you need to process the code. Now with Tau's runtime preloading tool, Tau exec, you can preload a wrapper interposition library that can intercept the runtime system calls, and you can substitute one call with another. And this is typically used to generate wrapper calls for MPI, OpenMP, even the POSIX IO routines and memory allocation and deallocation routines. The advantage is that you don't need to modify the binary executable. And once your Tau exec inserts the Tau library, you can enable other Tau options such as generate the communication matrix display, or generate OTF2 traces, or generate event-based samples. We also have support for the OpenMP tools interface in Tau. OMPT is a relatively new interface, and it allows you to insert the hooks at the thread boundaries and assess the synchronization calls and see when a parallel region is entered and exited. So there are a couple of different versions of this TR standard, and Intel 18 implemented the TR4, and Intel 19.01 had the TR7 support, and we also have support for the latest OMPT version 5, which is now available in Intel 1903 and newer compilers. It's also available in Clang 8 compilers, and we will demonstrate the use of this OMPT version 5, which is now being implemented by these compilers. So in the demonstration, I'll show you that instead of just launching a job with, say, apprun a.out, you can launch it with apprun Tau exec a.out. And here, this will generate data at the MPI level. Now, if you have an application that is compiled with -G, you can also enable event-based sampling by saying -EBS. And you can also specify, besides wall clock time, a hardware performance counter from PAPI by specifying the EBS source and the overflow counts and even the resolution, whether you want the event-based samples to be collected and represented at the file level or function level or the line level. The statement or the line level is the default. You can enable IO tracking by the Tau exec -IO flag, and you should use the -T or a tag flag to identify a specific configuration of Tau. For example, if you have built a number of different configurations and you want to say, I want to use the OMPT configuration with version 5 support, with PDT for source instrumentation support, and MPI, and then enable the -OMPT flag for tracking the OpenMP runtimes. You can also have other flags like memory debug and loadlib. So it's important to note that we inject the Tau DSO in the executing application. This requires a dynamic executable, which is typically generated on the Cray Intel systems with the dynamic -dynamic linker flag. And then you use Tau exec while launching the application. You may want to load the Tau module when you start. And here is an example. There's a workshop tarball which has several examples in it. You can just go to this NAS parallel benchmark, see the file, launch it with make clean, make sweet. In another window, you can launch Tau after allocating a given node, and you can specify your project ID to use in that case. And you can launch it using apprun with this, or when you're using Tau, you can just launch with Tau exec with the tags of OMPT and enable the OMPT support like this. We can also add the -EBS over here to generate not only the OpenMP level instrumentation, but also the samples collected at the source level, the statement level. And then you can pack a particular profile file, profile data set using paraprof --pack. Remember, you need to have a module load tau command before you can use the tau exec or paraprof commands. And then on your laptop, you can launch the PPK or the compressed profile file. So I'll show you an example of a typical multi-threaded MPI with OpenMP application, say the NAS parallel benchmark. There are benchmarks there, LU, BT, and these are written in Fortran with support for threading. And it solves, the BT benchmark solves a discretized version of the unsteady compressible Navier-Stokes equation in 3 dimensions. So you see the data along the X, Y, and Z dimensions, and it performs these 200 time steps on a regular 3-dimensional grid. And here is the Fortran compiler specified as FTN. You need to make sure that the -dynamic flag is there. And then when you make it, you can say make suite, and it will just compile a given configuration. And you can also use source instrumentation if you substitute the name of the compiler with, say, tau F77. But I'm going to show you the tau exec tool first, where you just preload the tau wrapper libraries and perform the measurements. And you can see that you can launch it with the event-based sampling EBS flag, or you can also use tau_sampling environment variable and toggle it to 1 with any of these. So here, what we'll do is we'll just go there to a make clean, make suite, do a Q sub to get a node, load the tau module, then launch the application using tau exec, and then on the head node, we can say module load tau and see the data. So here is a node that has been allocated. I can say make clean and say make suite, say -J, and it will compile the application with this -Q OpenMP flag. I am on theta here, and it uses this -dynamic flag to then generate the executable. So now I have in the bin directory a binary. Now, here is the launch command. First of all, you must load the tau module. I set the number of OpenMP threads to 4. And now this uses 16 ranks, and so we are just using one node. It fits in perfectly with 64 cores. Here, I'm saying apprun -n16, and then setting the environment variable OMP num threads, passing on the -J, -D, and -CC depth. Now the CC depth is really important to bind the OpenMP threads to physical cores. If you forget to set this, you will find that a lot of time is being wasted in like a schedule yield call or something. And then I just run an uninstrumented application like this. So let's just run this without tau first, and I'll just run -R, and it will run on 64 cores with 16 MPI ranks and 4 threads. And now it's done running. Now, to run it with tau, all I do is, instead of using the application like this, I will add the tau exec, and I'll say OpenMP tools interface OMPT version of tau with V5 and enable OMPT. I'm also enabling the event-based sampling here and then launching it. So here is the execution with tau now. And what it will do is it will intercept the OpenMP calls transparently. You will see the time spent in MPI as well as OpenMP calls, and it will generate a set of profile files. So here if I look at the listing, I see the profile files which says this is rank 15, thread 1, thread 2, thread 3, and thread 0. The 4 threads. Now I can pack a file and I can say the ppk directory which I have mounted on my local laptop, and I can say bt ompt.ppk, say, and it will create this compressed file. And now I can just say paraprof bt ompt.ppk, and I can then launch the tool to view the data with the graphical interface. We also have a PProf tool, which is for text-based visual display of the profile data. And here, if I open up the thread statistics table in ParaProf, I can see the inclusive time spent in it, exclusive time. I can sort it by the inclusive time like this. It says about 10.7 seconds were spent in this, and then it shows you the breakdown of 2.8 seconds were spent in the ysolve and the OpenMP region associated with that, and Xsolve, and I can even go down deeper and see exactly what was happening in the ysolve region. So here I can see an individual source location. Here I can just expand this and show you the line number. So it shows you the total time spent, like 1.5 seconds are spent in this region, and you can see the source file. So that's this particular loop. So it's right down to this do loop that we can see exactly where it was spending time in this source, and it's in a multiply nested do loop over here. And if you want to see this particular loop, you can see it with the OpenMP. So this kernel name is generated by the compiler, the Intel compiler, and you can see the exact OpenMP do loop where it says it spent this amount of time. So it allows us to look at the time spent in MPI calls, in OpenMP calls, and even down to the source level. And you don't have to do much to use this. All you had to do was change the script to launch the application, which is linked with the dash dynamic flag with the tau exec tool. Now we saw this Fortran example. Let me just go to a C++ kind of an example. Again with OpenMP, I can say make clean, make -j, and it launches the compiler with the -q OpenMP flag, and you can see that this application is built. And if I just launch it without tau, with a module load tau, and the OpenMP is launched like this. Here I have the CoMD OpenMP MPI application, and I set the number of threads to say 2. And then again, I set the -j, -cc, depth, and then -d parameters. The -d parameter should correspond to the OpenMP number of threads. And then just launch a particular configuration of tau with the OMPT and event-based sampling. And here is the MPI, OpenMPI with OpenMP running with tau exec. And here is the execution. I can say paraprof, packet, put it in a directory, say CoMD, OpenMP, tools interface, and pack it in this file and launch it with ParaProf OMD ompt.ptk. If you don't specify the -t tags, you will see that it will just show you the MPI configuration by default. And here are the work loops. There is a specific sample. You can go down to a particular sample and see exactly where it is in the source code. And there are other views that you can see, other windows in ParaProf, where each color represents a particular function of execution. And we are able to then go down to a specific source line number and see that in this loop, at this particular line, it was spending so much time. And you can see that there's a for loop which is nested. There are like 1, 2, 3, 4, 5 levels of for loops, and this is the exact location where it's spending this time in a function called LJ force. This is the CoMD application, molecular dynamics code, and it shows you the interaction between the specific atoms over there. So with that, let me go back to the slides and say that you can generate different kinds of profiles. You can create a flat profile which doesn't show you the caller-callee relationship. You can generate a call path profile, even a full trace of the application. And there are environment variables like tau call path depth, and even a tau call site, a variable that will show you where the time is spent at a given source location, and phase-based profiles. So ParaProf is the browser that I described. You can even stack these bars together so each function has its own space and look at the time spent in a particular thread of execution. This is a flat profile. And here I am showing the thread statistics table. You can sort by clicking on those columns. You see the source code over here and see how much time is being spent. Now, this is important to note that the exclusive time in the application here is 9.1 seconds, but sampling can show you 9.0 seconds of the total time by the samples that are collected. And that's okay for these to be slightly different. But here are the samples shown on different threads by enabling the sampling. Here you can look at the Callstack sampling, so you can see exactly where the application is spending its time along a given call stack, and you can unwind it to go deep down, and you can even see what's happening inside a particular runtime system call, like the MPI stack can be shown over here. Now, event-based sampling with unwinding turned on, enabled by this environment variable, EBS unwind equals 1, is more expensive than just collecting samples. So you can enable call site tracking using tau call site equals 1 as shown here. So you can see that MPI received took 14 seconds, 14.6 seconds, but 12.6 seconds out of that came from this function called exchange1 at exchange1.f at line number 68, where the MPI receive call was running. And this is what happens inside the MPI receive call and where it was getting called. So immediate parents and then immediate children for a given function shown by this arrow in the call path thread relations window. You can see more details down. You can jump to a particular function and see where it was getting called from. And then look at the overall breakdown of that call site, where else it got called. We can also create context events in tau where they are not bracketed with a start and a stop, but triggered with a data item at a given point. Here we are seeing along a call stack what was the write bandwidth obtained for a given file and how many bytes were transferred, what was the megabytes per second, and how it varied during the execution with the mean, max, min values, the bytes written to each file. Here is the 3D window in ParaProf. It can show you the visualization along the MPI ranks. It can show you the names of functions and where time was spent. So you can now see the shape of a particular profile and see hotspots, and then identify what was going wrong at a given thread, and see exact the function and thread IDs, and even look at the variation of the height and color that you can pick over here. Is the 3D visualization window that's enabled by going to the Windows menu, and then you can see the 3D display. Here we see the breakdown of the time spent in the xsol, ysol, zsol functions. And if you want to do more detailed instrumentation, you can do source instrumentation using PDT, where the tau instrumenter analyzes the source code, the application source code, creates an instrumented copy, and you can specify what to instrument or not. Here you need to set an environment variable called tau makefile. This identifies a given configuration of tau, whether it is to use Intel compilers with profiling with PAPI or MPI or OMPT like we saw with the -t. And these tags are the same as the -t parameters. So when you install tau, you can typically configure it with PDT, tell where PDT is located, and enable the BFD, unwind, and IO wrapper flags. And once you install it, you can set this tau makefile and just use the tau compiler scripts instead to compile your program. And we also have installation on the laptops where you can install it. And if you just load the tau module and look at the makefiles, you will see that there are a number of makefiles. This one, it has support for Intel compilers with PAPI, with MPI. This also supports pthreads. This supports the OMPT version 5, and this is without MPI. So if you had an MPI application, you could specify the Intel, PAPI, MPI, PDT in the tau makefile, compile it with these compiler scripts, and then just run it with AppRun and create data sets, pack it if you want, launch ParaProf. What's important to note is that when you configure it, say with PAPI, it creates a makefile with a -PAPI in its name and puts the libtau.so, the DSO, in the shared PAPI MPI PDT directory. If you configure it without that, it creates something like this. So with tau exec, I can choose a specific configuration of tau with the -t PAPI or without that. And by default, it uses an MPI configuration, which is shortest. You can also use the -s flag to see what will happen without running the whole application. If you choose to compile the application with the tau scripts, you can also set optional tau options, environment variables, such as tracking IO or selecting a specific selective instrumentation file to give to the tau instrumenter, using tau's shared library instead of the static library, etc. Here is the selective instrumentation file, and you can see over here that you can have a selective file with an exclude list of functions. And then you can also generate such a list directly from ParaProf, where it looks at the throttled functions, the functions that were trivial and took a lot of time. By saying create selective instrumentation file and then saving it, you can also change these thresholds for time per call and the number of calls. And then once you install and use this with the tau makefile set like this, you will be able to create instrumentation at the source level in all the files and select the tau options. We also have support for runtime options. You can set the selective instrumentation file, you can enable sampling, you can turn on tracing or call path, or specify a given call path depth, or even a call site profile like this. If you have a configuration with PAPI, you can set tau metrics environment variable to pick a PAPI counter, like selecting PAPI floating point instructions along with time. You can set these counters to these environment variables to, for example, select selective instrumentation file. So you can do the filtering at runtime. You can also specify OpenMP level of support and memory debugging capabilities in tau. So you can download tau from the tau.uoregon.edu URL. We also have a project called Tau Commander, which simplifies the use of tau. Tau is also available as part of the E4S Extreme Scale Scientific Software Stack, and we have containers built for HPC, Singularity containers can be launched on Theta, and then they already have Tau installed in them. Our development work goes on at the Performance Research Lab at the University of Oregon, and we have an active visitor program. You can come visit us and work with us in Eugene, Oregon. And I would like to thank our sponsors, the Department of Energy, Argonne National Labs, Office of Science, the Exascale Computing Project, the LBL, SIDAC, the Tri-Labs, Livermore, Los Alamos, Sandia, PNNL in Oak Ridge, and the Department of Defense, National Science Foundation, NASA, CEA in France, and our partners at the University of Oregon, Ohio State University, ParaTools, University of Tennessee, Knoxville, TU Dresden, and ULS Supercomputing Center. And this was supported by the Exascale Computing Project, and I thank them for their sponsorship. Thank you.